So I want to do the example that we looked at in the last video in our more streamlined 6-step process. And before we start, I want to remind you there are two methods to do this problem. There is the p-value method and the critical value method. Generally speaking, you do not need to do both methods. You pick one or the other. On the homework, for example, they'll specify whether they want you to use the critical value approach or the p-value approach. For this example, I'm going to do both just so we can get practice doing both. So let's take a look. So our first step on any one of these hypothesis tests is to state the null and alternate hypothesis. And so, step 1, state the null, oh come on now. Apologize. State the null and alternate hypothesis. So rereading the question, it says that the average ACT score is 20.8 with a standard deviation of 4.8. But this ACT test prep company claims that their students have a higher average score. And as evidence, they show that a sample of 80 of their students has an average score of 22.3. Can we conclude that their students scored a significant score higher? Let me sneak that in there. Score higher at a significance level of 0.05. Okay, so the null hypothesis is that the answer to that question is no. Their students score the same as everybody else. And the alternate hypothesis will be the one that is supported by the evidence, which suggests it looks like they really do score higher. So in this case, mu equals 20.8 will be our null hypothesis. This says that we think mu, the average score of their students, is exactly the same as the average score of every other student, even ones that don't take the test prep company's preparations. The alternate hypothesis says, no, we think that in fact it is effective, and this is what the evidence shows. The evidence shows that their students have a little bit higher score, but again, this could totally be a fluke. Maybe it's just a luck of the draw in the sample that they happen to take. This is a right-tailed hypothesis, and we will use that going forward. So the second step is we need to define what we're going to consider weird. And we have two ways to do this. If we're doing the p-value approach, weird is just basically what area or probability we're going to consider weird. So we just need the significance level, which is alpha equals 0.05, is the probability we consider weird. And if we're doing the critical value method, then what we look for instead is the z-score. So the critical value, which in this case is going to be z sub alpha. I know this is the notation to use because we've got a right-tailed hypothesis. So z sub alpha, all the area is going to be in the right tail. It'll be a positive z-score. Z sub alpha is equal to find this value, we have to go look at our table A3. And so here's our table A3. We are interested in an area in the right tail. In fact, maybe let's draw the picture first to get a sense of what all of these pieces mean. And then we'll go to that table. So here's how we are picking it out. So it hopefully makes a little bit more sense. Here's our sampling distribution of all the different possible x-bar values. And we're assuming the center of this is at 20.8. That is our null hypothesis. And here is the region that we are going to consider weird. It is the top 5% of the area. So here is the area, alpha equals 0.05. And here's our cutoff. Over here are results that are weird, and over here are results that are not weird. And so we have defined this region that we're considering weird So far we've defined it by its area. For the p-value method, we just defined that area. Let me go back and correct that letter there. And now I need the z-score that defines that region, and that is our z sub alpha. And the z sub alpha is going to be the z-score that cuts off the top 5% of the area. So now if we go over to our table, this will make more sense. I want the z-score right here, so I want, in this case, the z-score, not t-score, where this area right here is 0.05. And so I go down and I look for the area in the right tail. Here's the area I'm interested in. That's the row or the column that I need to use, but I need to use the row. Let me zoom this out a little bit. Labeled z, because again, we're dealing with a z-score, not a t-score. And so that tells me the number that I'm using is right there, 1.645. And that's how we use that table. So real quickly, this number is 1.645. So now what we've defined what's weird via both its area and via z-score, and now we need to look at our actual evidence. So the third step is we need to compute the test statistic. And the formula for our test statistic, it is a z-score. We take the value of x bar, subtract off the presumed mean sitting right here, there's our mu 0, and then divide by the standard error, which is sigma over the square root of n. And so for us, that's 22.3 minus 20.8, whole thing divided by 4.8 over the square root of 80. And all of these numbers just came from the framing of the problem. Here's our mu 0, here's that standard deviation sigma, here's the x bar, and here's the sample size. Those are the numbers that I just plugged in. So these are all given, and this gives us approximately, toss parentheses around so it's easier to compute on the calculator, this gives us approximately 2.80. So we've got our test statistic. Step number 4. If we're doing the critical value method, we get to skip this step because we just need to find the things that we're going to compare. I've got my two z-scores already, so I'm going to skip this step. But if we're doing the p-value method, I need two areas to compare. So the critical value method, I'm going to compare this z-score to this z-score. We've got them both. For the p-value method, I'm going to compare this area we're about to find, the area of my p-value region, with this area up here, which is alpha equals 0.05, the entire region. So we just found basically right here is where our actual, this worked out to be 1.645. This number right here turned out to be z equals 2.80. And now I'm trying to find the area of that region. That is going to be my p-value. And that's what we want to find now. So what is that area? We're going to be able to use table A2, so find the area. If I can get this to work, find the area to, in this case, the right of z equals 2.80, which is the p-value. So we've done this before. We can use table A2. I believe I deleted that from here. Let me add it in real quickly. I need to add in and to have this already in there, I just need that page, skip that page, insert those. Okay. So let me reorganize things, just get these in a place where they aren't covering up everything. So this one I don't want, that one should be gone. Just delete that one. And let me pull these guys over to the side over here. We'll look at them in just a minute. Okay. There we go. So I want the area to the right of z equals 2.8. We have two ways we can do that with our tables. I can find the area to the left of z equals 2.8 and then do 1 minus that number, so 2.80. Here's that number. I can do 1 minus this, or alternatively I can recognize that the area to the right of z equals positive 2.8 is the same as the area to the left of z equals negative 2.8, and I can just look up z equals negative 2.80 as we did in class, and there's the number right there. So either of these two numbers, here's the z equals negative 2.8 number, z equals negative 2.8, or I can do 1 minus the z equals positive 2.8 number, do 1 minus this number. Both of them give the same result. That area is the p-value, and the p-value is 0.0026. I'll go fill that in our picture up here, 0.0026. So now we're going to decide whether or not we're going to reject the null hypothesis by deciding if our result is weird. So is our result weird? Well, we can tell from the picture clearly. Here's where our result fell, right here. Let me do it in another color, right here. That's definitely in the weird region. So the answer is definitely yes. And the criteria that we can use to answer that is as follows. We know it's weird because according to the critical value method, the test statistic, which was z equals 2.80, is more extreme than the test stat. Sorry, not than the test stat, than the critical value. Than the critical value, which was z sub alpha equals 1.645. So there's the criteria that we're using if we're talking about the critical value. If we're doing the p-value method, we likewise know our result was weird because our p-value, which is 0.0026, is less than 0.05, which was our value of alpha, our significance level. So there's the criteria. We got a weird result. Because our result is weird, that means we should reject the null hypothesis. They're only weird under the assumption that the null hypothesis is true. So, we get rid of that. Going back up to the null hypothesis, the null hypothesis stated that we think that the average score of these students that take this test prep class is really the same as everybody else. We just rejected that idea. We rejected the idea that the average score of these test prep students is also 20.8. If we rejected this, what we're going to do instead is accept the alternate hypothesis that their scores really are actually higher, that we think mu is greater than 20.8. And so, doing this, let me undo that. In plain English, we just rejected the idea that we have strong evidence that suggests that their scores are in fact higher. That 22.3, that was really unlikely to have happened by chance. The probability that x bar equals 22.3 is a fluke, that it happened just totally by chance, it's only 0.0026. About 0.25% chance that it's a fluke. Very unlikely to have been a fluke. With that in mind, because we've rejected the null hypothesis, we say that the evidence strongly suggests that the test prep actually does So the test prep company students do in fact have higher scores. So this is the idea. It's a sentence, a plain English sentence. The evidence suggests that the test prep company students do have higher scores than the average other students. And so going up to this, can we conclude that their students score that their students do score higher? The answer is yes. We can conclude that their students score higher. It's very unlikely that those results were just a fluke. Real quickly, let's also do this problem on the calculator. So on the calculator, we're going to get to the same list of tests that we use for our confidence intervals. So we're going to hit the stat button, go over to the list of tests, and the test that we're going to look for in this case, because we're using a z-score, and because we're doing a hypothesis test, we're using z-test. So select z-test. It should be the first option on your calculator. And we'll use the stats button, right? So as before, it'll ask whether we want to use data or stats. I'm going to use stats, and it'll ask for all of these values. It'll ask for mu sub 0, it'll ask for sigma, it'll ask for x bar, and it'll ask for n. And lastly, it'll ask for what is the form of our alternate hypothesis. So our alternate hypothesis is mu is greater than mu naught, right? Ours was right-tailed. So plugging these values in, our mu naught, this was the 20.8. Let me plug that number in, so 20.8. Sigma was 4.8. X bar was 22.3, and n was 80. Let me enter all of those numbers in. And skip the thing where it asks about the color and hit calculate. We don't want it to draw, we want it to calculate. It gives us two pieces of information that we can use. It gives us z equals, so the second thing that we need after the mu, is the first thing that says mu greater than 20.8, but then it gives us our test statistic. Z equals 2.79508497 whatever. This is the test statistic. It computes it for us. The next thing it gives after that is the p-value, p, 0.002594336. That's the p-value. It gives us the two things that we would need. We still have to decide what we decide or what we are going to consider weird, but it gives us the test statistic that we would use if we were doing the critical value method, and it gives us the p-value, which we would use if we're doing the p-value method. We still have to decide what to do with this number. We still have to come up here and use these values in the context of one of these two scenarios right here. So it gave us this number and this number. We still need to decide what we're going to use for this number and this number. But those are both taken care of in step 2. So it basically does this step for us and this step for us. It does steps 3 and 4 for us on the calculator. We still have to do all the thought and write out our conclusion in plain English once it's all said and done. The next video, we will jump ahead to section 9.3, where we'll do another hypothesis test for the mean, but this time with sigma unknown, and it's going to be the exact same type of thing. We're going to do what we did in chapter 8. Everywhere sigma shows up, we're going to replace it with a s. Everywhere that z shows up, we're going to replace it with t. we're going to use a t-distribution instead of a normal distribution. But otherwise, these same 6 steps will hold in section, there we go, let me zoom out, come on, there we go. Those same 6 steps will hold in section 9.3 as well. Again, everywhere that a z shows up, we'll replace it with a t, and everywhere that sigma shows up, we'll replace it with an s, and we will have to take into account degrees of freedom when we use our table A3. Okay, I'll be making that video soon. In the meantime, good luck.